Hello. In the previous lecture, we were doing revision of wave mechanics. In this lecture also, we are going to continue with the same. That is, we are going to see some important aspects of wave mechanics in the series of revision to wave mechanics. I would like to tell you that we have already done a good amount of wave mechanics, but all these lectures are to actually inculcate in you a little bit of thinking and a little bit of what has been asked in the exam. You should understand uh, those points also. Okay. Okay. So as you're aware that in classical mechanics, the motion of particle is usually described using the time-independent position, time-dependent position. So basically, whenever it comes to classical mechanics, you have some time-dependent position vector, okay, which acts as a dynamical variable. So it acts as a dynamical variable. Or probably when you are working in space, instead of position, you'll have some momentum. Okay, corresponding to this in wave mechanics, that is in quantum mechanical version or wave mechanical version of quantum mechanics, the dynamical variable the dynamical variable in wave mechanics is the wave function. In general, understand that this particular wave mechanics, in this particular wave function, belongs to the set of complex numbers, or in general, it is a complex valued function. This particular wave function satisfies something called as the Schrodinger equation. Which looks like this. Okay, so basically, this is a Schrodinger equation for a non-relativistic relativistic particle moving in x-axis along x-axis of mass m while acted upon by a potential. For most of our studies in this particular lecture series, we are going to consider potential to be time independent. So most often, here in this course, we are going to consider V generally only as a function of x, not as independent of time. So we're going to consider the potentials which are independent of time. Now, just think why this particular wave function. Just think about this. Why wave function that is psi x comma t or psi r comma t if I write in 3 dimensions also, belongs to complex set of complex number and not real numbers. See, if your wave function was real, see, wave function was a real valued function, then just consider the Schrodinger equation. So if my this particular thing is real, so let's say this is real, this is already real. If psi is real, then this product must be real, right? And if psi is real, then the derivative, the second derivative must be real. So this is also real. Had it been a real thing, then the derivative is real and it is multiplied by iota h ket. So this goes imaginary. So therefore, so one of the things that you can clearly see from your Schrodinger equation, that psi being real will violate this particular this particular Schrodinger equation. Okay, because the right hand side would be completely real and the left hand side would be imaginary due to this explicit factor of iota being attached to it. So clearly, one can say that psi cannot be a real function. Okay, two very important things that you can figure out from this particular equation that are very important. One is that you know that this particular equation, you can say that this is a first order differential equation in time. So you can say that the Schrodinger equation is first order in time, a first order differential equation in time. And what is good about it? See, if you have this first order differential equation, and if you have given some initial condition, okay, some initial condition, then the wave function can be determinable for all other times. So let's say if wave function is defined at some time t equals to t naught. Initially, if you know that, let's say t equal to t naught, you know the wave function. So if some initial conditions are given, then psi can be determined for all future times. Okay, this is one thing. Secondly, uh, for linear differential equations, one property is very much clear that if psi1 and psi2 are solutions, then a1 psi1 plus a2 psi2 is also a solution. These two properties are very important because see, lately we are going to use this okay, is also solution. That is here a1 and a2 belongs to, let's say, set of complex numbers. Let a set of complex numbers. So first thing is clear that Schrodinger equation is a first order differential equation in time. That is at some time, if you know, let's say at t equal to t naught, you know the wave function, then you know it, you can determine it for all future times. Okay, because once you know initial condition, then because you know that if you're solving a first order differential equation, then you may get an arbitrary constant, and that arbitrary constant can be found from some initial condition. And secondly, because it is linear, so psi1 and psi2, if they are solution, then a1 psi1 plus a2 psi2 is also solution. We've already discussed it quite amount of times that the psi in general is a complex valued function. However, the psi mod whole square, which is psi star at a psi conjugate times psi, holds some physical meaning. This holds some physical meaning, and the physical meaning of this particular thing is that it represents the probability, it represents the probability density. Okay, and indeed, this probability density has to be a positive definite quantity. It should be a positive quantity, right? Okay. Now, let's say in one dimension, if I'm saying I've already taught you, but still just writing it for you for the sake of revision, that this particular probability density, when multiplied by dx, gives you the probability of finding the particle between x, comma, x plus dx in time, let's say t, at time t, let's say. Okay. And we know that in order to normalize it, we've seen from the global conservation of probability that this particular integration from minus infinity to plus infinity, this dx psi x comma t mod whole square comes out to 1. That is probability of finding the particle in all these tiny intervals when integrated together gives you a 1. Because anyway, the particle should be found somewhere in the space, right? Okay. One of the things that we've already seen that by global conservation probability states that by global conservation probability, global conservation of probability, we know that the Schrodinger equation guarantees that once normalized, the wave function once normalized remains normalized forever. Okay, so these are some important things that we've already seen. Okay, now let us just pay our attention to one of the most important conditions, which are called as the bonds conditions. Okay, so these are very important conditions. We studied them in a little bit of hurry when we were doing it. Now let us just pay a little bit more focus when we are revising these concepts. Okay, okay. So this particular thing, that is psi mod whole square being interpreted as the probability density for finding the particle in a given, let's say, state at time t, is known as the Bond's probabilistic interpretation. So this representing the probability density for finding particle or a system in, let's say, at some point x or in some state at time t is known as the Bond's probabilistic interpretation. Now, Bond's contribution is just not this. Bond's contribution is just not this. Rather, he also proposed four conditions on the wave functions which are used in finding many solutions of the Schrodinger equation. So basically, he also gave four conditions. And these four conditions are the conditions on the physically realizable wave functions. Okay, so four conditions. Okay, the first condition, let us first write just for sake of writing. So we know that these four conditions are applicable on the wave function which satisfies the Schrodinger equation, which is given by this. Now, these four conditions are these like this. I'm going to write them up. And at times I've found that questions have come from this particular section. Okay. So please do understand that this is an important zone. Just pay attention to this. Okay. So the first condition is that the wave function must be single value. So I'm just writing psi, uh, let's say in 3 dimensions or 2 dimension. First step, I'm just writing in 1 dimension. One can also write it in 3 dimensions also, but just writing in 1 dimensions. Okay. So psi must be a single valued function. Why it must be a single valued function? Because it must have some unique value at some point. Okay, because if it does not have unique value, then at a point you may have two probabilities. So basically, this particular postulate guarantees it guarantees that there is only a single value for the probability at a given time and at a given state. Okay, so a single value for the probability of the system being in a given state. Okay. The second thing that follows from the bond condition itself, probabilistic interpretation itself, that if at all the psi mod whole square represent, let's say if I'm integrating on tau, let's say I'm doing on a 3 dimension, then it should be 1. If I'm doing from minus infinite to plus infinite psi mod whole square dx, then it should come as 1. The first condition that is important is that this particular function should be integrable. So another condition is that the wave function must be square integrable. The wave function must be square integrable, because if it's not square integrable, then the wave function, then this particular wave function mod whole square would not be, the integration of this wave function psi mod whole square will not be finite. So in other words, one can say that this integral must be finite. It must be a finite integral. Okay. So understand that this particular integration should not go to infinite or zero. Uh, Otherwise, if it goes to zero, then the probability of finding this particle would be finding particle or a particular uh, system in a given state is cannot be zero, right? So because understand the psi mod whole square dx, because this is being integrated, it has to be greater than equal to zero. However, it cannot be equal to zero. Neither it can be infinite. So it has to be finite. And one consequence of this proposal that we are also going to see a little bit later also. So one consequence of this proposal is that the wave functions must go to zero as x tends to plus minus infinite. As x tends to plus minus infinite. Okay, so this is one of the most like one can see that if it does not go to zero as x tends to infinite, so it implies that the particle, if it does not go to, so if it happens that mod of x tends to infinite and psi of x does not go to zero, it implies that the system is unbound. So for energy, for bounded systems, uh, one of the condition that follows is that as x tends to plus minus infinity, psi x must be tending to zero. Because if at x equals to plus minus infinity, that is at a large distance also, there is some wave function. There is some wave function left. So basically, it implies that the system cannot be bound. So one of those conditions, one of the things that we follow from the square integrability of the function is that psi x must tend to zero as x tends to plus minus infinite for bound systems. Third, the wave function must be continuous everywhere. The wave function must be continuous everywhere. That is, there should not be some sudden jumps in the probability density. Okay, so there should not be sudden jump. Okay, if there is a sudden jump, that implies that there is a sharp discontinuity. So basically, okay, so basically, if there is a sudden jump, then it would imply there is a sharp discontinuity. And if there's a very sharp discontinuity, the derivatives at this sharp discontinuity would be infinite. There would be infinite derivative at these points. So let's say, just for an example, I'm showing by an example of 1 over x. So let's say if 1 over x is there, I know that as x tends to 0, there is a sharp discontinuity. So you can see that there is an infinite jump of discontinuity here. As x tends to 0 minus, this is tending to minus infinite. As x tends to 0 plus, this is tending to 0. So basically, this is a sharp discontinuity here. If you take the derivative of 1 over x and try to find this value at x equal to 0, you can see this derivative would go towards minus infinite. So clearly, there would be an infinite derivative at these points of sudden jumps, you can say, or you can say sharp discontinuity. Because see, if the function has a discontinuity, such as very sharp step or some sharp, if it if the function possesses some sharp discontinuity, it can be seen as a limiting case of a very rapid change of the function. And such a rapid change would mean that the derivative of the function is very large. So basically, rapid means what? Just change. This particular change has happened, and very large change has happened. So basically, it could imply an infinite derivative. And infinite derivative, in turn, would violate my condition number 4, which I'm writing here. So therefore, one must understand the wave function must be continuous everywhere. The fourth condition is that all the first order derivatives all the first order derivatives of the wave function must be continuous. Okay. So one thing is clear, that the wave function must be continuous everywhere. Why? Because the wave function must be continuous everywhere implies that there is no sudden jump in the probability density. So there is no sudden jump in the probability density while moving in the space. Because if a function has a discontinuity, let us say like a sharp step upwards or downwards, it can be seen as a limiting case of it can be seen as a limiting case of a rapid change of the function. Such a rapid change would mean derivative of the function being very largely positive or very largely negative. And in the limit, let's say I just use a step function. It's just a step function. So you know that for all x greater than 0, this is 1. At x equal to 0, we define it. At x equal to 0, we define it as 0. So basically, if I want to take the derivative, I know this is a vertical derivative, right? The derivative would come as infinite. There would be an infinite derivative at this point. You can do it using the ab initio method. So if I want to find the right-hand derivative, left-hand derivative and right-hand derivative, one can see that there is a sharp discontinuity here. So there is a sharp discontinuity here. So your derivative will not be defined, or the derivative will be infinite derivative for these you can say functions where you have this sharp step kind of thing. Okay, so if the derivative is infinite, then you can also say that we've seen that the momentum operator is is actually a derivative operator only, and then this would imply an infinite momentum, which is not again physically realizable. Or otherwise, it will violate our condition number 4. Our condition number 4 is that all the first order derivative must be continuous. Let's say if this 1 over x is the function, I know that this particular thing, minus 1 upon x square, goes to minus infinite as x tends to 0. Okay, so clearly you can see that this is not a finite valued thing. So basically, an infinite derivative does not lead to any uh, physically realizable, does not lead to physical realizability. So one can clearly see that infinite derivative would imply an infinite momentum, or you can say that it will violate the condition number 4, which suggests that all the first order derivatives of the wave function must be continuous. Because if there's another way of looking at it, because if the derivative is, so I'll write, if if the first order derivative, let's say psi dash I'm writing, it is discontinuous, then one cannot define the second order derivative, right? One cannot define the second order derivative. Because if first order derivative is discontinuous at a point, then at that point, the function would be non-differentiable. So your second order derivative is either not defined, or you can say that there would be an infinite second derivative. And one knows that in order to quantify the energy, you have this operator. This being infinite implies an infinite energy, which is again non-physical. Okay, so one has to understand the wave function must be continuous, and also the first order derivative must be continuous. Also, first order derivative must be continuous. Okay, just look, we will see there are a few exceptions also to this condition. Don't worry about it. But right now, we are just focusing on what was bonds, you can say conditions. Basically, what were the bonds condition? We are just fixing on that. Okay, I hope this is clear. Okay, so now let us move to a few ways of understanding, a few questions, or you can say few things. So just think about this. So can these wave functions be applicable? Can these wave functions be applicable for a particle for a particle in a bound state. Okay, here n is a constant and alpha, beta are greater than 0. Just think about this. So let's say if I'm giving you the wave function, let's say psi, as a function of r in 3 dimensions, like e raised to power minus of alpha r upon, sorry, r cube. Do you think that this particular wave function uh, represents a bound state? Do you think that this particular wave function represents a bound state? So indeed, you can see that this wave function goes towards 0 as x tends to infinite, as r tends to infinite. Understand that whenever you have this exponential, because alpha is positive, so this is 1 upon e raised to power alpha, there is r cube on the denominator. If you write it as 1 upon e to power alpha, so indeed it goes to 0 as r tends to infinite. Also that this is continuous differentiable, this is continuous as well as differentiable, so there would be no as such problem, the quotient function. The problem is this particular thing. At r equal to 0, this will become infinite, or you can say at r equal to 0, the wave function is singular. So therefore, this cannot be physically realizable wave function for a particle in a bound state. Okay. Uh, Let us move to another just an instance. Let's say I just take another wave function. Let's say psi as a function of r, given by n times 1 minus e raised to power minus of alpha r. Do you think this particular wave function is physically realizable? Again, the problem is that as r tends to infinite, this wave function does not go to 0. See, it goes to n. Since it goes to n as r tends to infinite, one can say that this does not represent a bound state. I told you, in order that your function remains in a bound state, the wave function should go towards 0 as r tends to infinite or as x tends to infinite, whatsoever may be the case. Let's say 3 dimensional or 1 dimension. But right now it is given in 3 dimensions. So for the bound state, one must understand that as r tends to infinite, your psi must go to 0, but it is going towards n. So this is again violating our condition as stated by Max Born. Do you really think that this function, wave function, which I'm just writing, can this be one of the cases which can represent a bound state? Okay, so psi as a function of r, for all r less than r, it is non-zero, and for all r greater than r, it is 0. Do you think that this wave function represents a bound state, or is this a physically realizable wave function for a bound state? The answer again is no, because clearly at r equals to capital R, this is discontinuous. So clearly this is also not physically realizable. You think this function, do you think this wave function represents a physically realizable wave function for bound state? Indeed, it does. Because see, this eventually can be written as what? This eventually can be written as r square. Okay, so basically, as r tends to infinite, we know that this would go to 0. because this is e to power minus beta r square, this is e to power minus alpha. Secondly, you can see that e to power minus alpha r and e to power minus beta r square both are infinitely continuous, or you can say both are infinitely differentiable function, and these derivatives are also continuous. You can see this. This is completely understood. We know that exponential in general is a continuous function, and we can differentiate it infinite many times. Okay, because e to power x derivative is again e to power x, and this is differentiable infinite times, and it is continuous. So it is infinitely continuously differential function. So I'll write it is infinitely continuously differential function from on R. Okay, so this is the class of functions whose derivatives are continuous. So infinite derivatives are also continuous. This is how we denote. So we know this. So we both are continuous as well as differentiable for all for in the entire real x on the entire real axis. Also that as r tends to infinite, psi tends to 0. And also one can find, one knows that the Gaussian function is integrable. We know that the Gaussian function is integrable. So basically, one can see that this particular thing can be written as n e to power minus of beta r square minus alpha r. So we can arrange it in terms of, let's say, I take beta common here. So I'll get r square minus alpha. So I can write r minus alpha upon 2 beta whole square. And then I can subtract and add some terms like alpha square upon 4 beta. I know that this particular thing is represents a Gaussian thing, and we know that this Gaussian is integrable from minus infinity to infinity. We know that this gives us root over pi by 2, and so following that we can always find this n. Okay, so it is clearly square integral. So clearly this indeed is a physically realizable wave function. Okay, so now let us take a few more examples to understand it better. So just think that a particle is of mass m is moving in one dimension with energy E, and let's say it is in the influence of the potential Vx such that E is greater than Vx. Okay, so let us consider a case where particle of mass m of energy having energy E is moving in one dimension, and let's say this in the influence of potential Vx such that E is greater than Vx. Then we are interested to find, then we want to find, let's say, we want to find which graph represent a bound state wave function. A bound state wave function. Okay, so let us take the first example. Let's say, can this represent a bound state wave function, this graph? Okay, no doubt this particular graph looks very smooth. This is a smooth graph. So basically it is a infinitely continuous and plus differentiable. This is not a problem at all. Okay, understand, whenever function is differentiable at a point, you will always find, let's say, some cusp or double loop. So let's say this cusp, if there is this sharp edge is there, the sharp edge is written technically cusp. So if this is the case, you know that this is non-differentiable at this point. However, if you have smooth edges, let's say like this resembles a graph of cosine. You can see, I mean, I have not drawn it to a perfect scale, but just understand that this is smooth graph. This is infinitely continuous as well as differentiable. But the point is that as x tends to infinite, the limit is not unique. In fact, the limit is oscillating. Limit is oscillating and it is not unique. And what Bond's condition requires is that as x tends to infinite, our wave function precisely should go towards zero. So clearly this cannot represent a bound state wave function of a particle of mass m moving in energy E under the influence of a potential Vx. Similarly, just think about this. Can this represent a bound wave function? Okay, so very much clear. Indeed, this is a graph resembling some x raised to power 2n. But uh, understand that this particular thing will go towards infinite as x tends to infinite. So psi would go to infinite as x tends to infinite. Clearly, this cannot be a graph of a physically realizable wave function. Do you really think that this particular graph can be a graph of a physically realizable wave function? Again, no, because see, I taught you initial also that this cannot be the case because it suffers an infinite discontinuity. Discontinuity at x equal to 0. So clearly, this cannot be the graph of physically realizable wave function. Can this be a graph? Just think about the possibility. Okay, just think about the possibility. Can this be a graph of a physically realizable wave function? Okay, indeed it is. Because see, as x tends to infinite, you can see that your wave function is diminishing towards 0, right? I mean, this is going to get asymptotic and it will approach your x-axis as asymptotically. Secondly, all the edges you can see, these are not sharp edges. So when for first order derivative, just remember this. So let's say if you have this cusp kind of behavior, that is, if you have this sharp edges, then one can state that here you do not have your first derivative. But here, this particular wave function is completely smooth, so it is continuously differential function. There is no as such sharp edges, so this is continuous as well as differential. Okay, and if you make the graph of psi mod whole square, so what will happen? This particular thing will go upside. So basically, if I do the mod whole square, so basically it is going to give us just the positive thing, and all this thing, you can see this area will come out as with this particular wave function. Mod would represent a bounded wave function. So this integral psi mod whole square dx would be something. It can be something. Right now, from the graph, I cannot say what it would be, but understand that if I just do a square of it, so most possibly I will not have this negative part. This will go upsides. And then I can integrate because this total integration is nothing but the area under graph. So one can think that this area would be some finite area. So one can say, yes, most possibly, this can represent indeed a wave function which is physically realizable. So this indeed can represent a physically realizable wave function. Obviously, this requires us a little bit more conditions to really assert what would be the probability and all those things. But right now, just on an abstract scale, just think about it that yes, it may represent. Although the first three examples clearly had violated some of the conditions of the max mod. So with this, I'm going to end this lecture. No, not end this lecture. Okay. So with this, you just let us come on to the little bit of exceptions. So one studies particle in a box. So one studies particle in box whenever whenever we start with quantum mechanics. If you're aware that one would start with you can say particle in a box, and we know that when we are discussing particle in a box, uh, the wave uh, you can say what I should say. Okay, so just give me a minute. Okay. So whenever one studies an infinite, you can say particle in a box, or you can say infinite square well, we know that the potential is given by zero, as x lies between some and infinite otherwise. So if this is the potential, we know that the wave function, here you have potential as infinite. Here again you have a potential as infinite. And here you have some potential. We know that the particle in this box, the energy eigenvalues are given by root over 2 upon a sine of n pi x upon. Okay, so basically, if you remember, just giving you, if somebody has known this particular thing, only then one can see this particular thing. Otherwise, one can skip. But understand that one knows that this condition, we are going to see it later on also. This condition is derived. This particular wave function is derived on the premise, or on the fact that wave function psi must be continuous. Must be continuous. Okay, but understand that, let's say if I just think of ground state. So let's say if I'm thinking of a particle in ground state here, psi g, it will be equals to root over 2 by a sine of pi x upon a. And this is one thing. And second thing is, here the wave function is zero, and here also wave function is zero. This is something those who have studied particle in a box or an infinite square well, particle in a infinite square well, must be knowing this. They must be knowing this. Okay, so they know that you know that this particular ground state wave function is given by root over 2 by sine pi x upon a, and here x psi is equal to 0. Here, let's say the wave function is prepared in ground state. Now, if I want to take the derivative, so I'll get the derivative as root over 2 upon pi, again pi upon a, cos pi x upon a. Now just try to take the left hand derivative. So I know that psi dash 0, psi dash z at 0 minus h would be simply 0, because here the wave function is clearly 0 because the potential is infinite. And to the right hand side, the wave function at 0 plus would be simply pi root over 2 upon a times root over pi. Clearly it is greater than 0. So clearly this is violating the condition number 4. Condition number 4, that is, all the first order derivatives must be continuous. Clearly this is violated. Okay, so therefore one arrives at a fact that this particle in a box or particle in an infinite square well is not a physically realizable system. Is not a physically realizable system. Okay, that is, there is no such mechanism. There is no such mechanism, or you can say there is no such physical mechanism which can generate an infinite potential well, an infinite deep potential well. Okay. So here I'm stopping. We'll see a few more violations like Dirac delta function, Dirac delta potential, where also you'll find that this the condition number 4 is violated. Okay. So indeed there are violations to all these conditions, but do understand that these are the conditions for the physically realizable wave functions. I hope I have made some sense in this lecture. Please do let me know if you're having some doubts in this lecture. Till then, take care. Bye bye.